Evaluate the volume under the surface given by f of x comma y equals x squared plus a half y over the region bounded by the curves y equals 2x and y equals x squared. So we have a region bounded by these two curves. So to find that region, we need to find the points of intersection of these two curves. Now at a point of intersection of these two curves, the y value is the same, okay, because it's a point on both curves. So we need to solve between these two curves. The y value is the same, so we just put 2x equal to x squared. If the y's are the same, then 2x must equal x squared. So we just need to solve this equation. Well, this is a quadratic equation, so we can factorize it like this. The product is 0, so we put each factor in turn equal to x equals 0. If we put the other factor equal to 0, x minus 2 equals 0 gives x equals 2. So at x equals 0, we have a point of intersection. And if we plug 0 into one of these, we get y equals 2 times 0, which is 0. So when x is 0, y is 0. So that's a point on the boundary of this region. And when x equals 2, well, if we plug 2 into, say, this here, we get y equals 2 times 2, which is 4. So when x is 2, y is 4. Now y equals 2x is a straight line. It's a linear function of x. So we can just connect these 2 points to get y equals 2x. Y equals x squared is a parabola. It's actually below the line for values of x between 0 and 2. It's either entirely below the line or entirely above the line. It can't be a bit of both, because if it did, it would cross the line at some point, so we would have 3 points of intersection, and that's not the case. We only have 2 points, as we've just seen. So all you have to do is just say pick one value, say x equals 1, and if you work out 1 squared, you'll get 1, whereas if you plug 1 into the equation of the line, you'll get 2 times 1, which is 2. So we know that the line is above the curve for values of x between 0 and 2. Now we could take cross sections of the region under the surface and above this shaded part, either in the y direction or in the x direction. So I'm showing one in the y direction. You could also imagine a cross section of the volume, say, taken in the x direction. Now we're going to do this by considering cross sections in the y direction, but later on we will do the calculation both ways. So we imagine an arbitrary point x lying between 0 and 2. What's the y value of this point? Well, it's obviously x squared, because it's a point on this curve. So I'll just write it in again. And the y value of this point is 2x. It's a point on the second curve, which is actually a straight line. So if we want to get the area of the cross section under this surface, this cross section taken in the y direction, we have to integrate from y equals x squared to y equals 2x. We have to integrate this function with respect to y from y equals x squared to y equals 2x. So that will give us a general cross section under the surface for any value between 0 and 2. And of course the next stage then would be to imagine summing all those cross sections from x equals 0 to x equals 2. That would involve integrating with respect to x. Okay, let's first of all get the area of this cross section at a general value x between 0 and 2. So again, you can imagine the surface is above this shaded region here, above or below actually, depending on what the function looks like. Well, actually it's positive here, but we're not too concerned about that actually, what the surface looks like. It turns out that the surface is actually out of the screen, above the screen. Okay, but let's see what's going on here. So this integral here will give us the area of this cross section. So we have to integrate x squared plus a half y with respect to y. So we're treating x squared as a constant. We integrate a constant with respect to y, we get that constant times y, so we get x squared y. If we integrate a half y with respect to y, well, we add 1 onto the power to get y squared, divide by 2, so we get half times a half, or a quarter y squared. Our limits of integration are from x squared to 2x. So we plugged the upper limit 2x in for y, because we're integrating with respect to y. Okay, I've just written it out here to make it a bit clearer. We have 2x by x squared, that's 2x cubed. We have 2x all squared, that's 4x squared divided by 4. It's 1x squared. Then we have a minus sign. Plug in the lower limit, which is x squared. That gives us x squared by x squared, that's x to the 4. And we have x squared squared here. That's x. We end up with a quarter x to the 4. So we end up with 2x cubed plus x squared, or x squared plus 2x cubed. And if we put these two terms together, we get minus 1 1/4, or 5 quarters x to the power of 4. Okay, so this thing here is the area of a cross section of the volume under the surface. A cross section taken at a general value x between 0 and 2. So if we could see the surface above the xy plane and just get, I can't see it here obviously, but we have the area at any value x. We have to sum all these cross-sectional areas now from x equals 0 to x equals 2. So we imagine summing them all, and that would give us the volume. As we've seen in previous videos, we multiply the cross-sectional area by dx, which is the width of a slice. Okay, so the width of this slice would be dx. If I project down here, this would be x plus dx. But anyway, I've kind of explained that before. Multiplying by dx will give us the volume of that slice, and we sum all those slices from x equals 0 to x equals 2. Okay, so we multiply the cross-sectional area by dx to get the volume of a slice, and we sum them from 0 to 2. So this is a straightforward integral. If you do that, you get 8/3. In this example, we are going to get the volume under the surface f of x comma y equals 5x squared y over the half of the unit circle that lies above the x-axis. So the unit circle has a radius of 1. So here's the region that we are integrating over. So like before, we can consider a cross-section of that volume in the y direction. So you can see that we're integrating from y equals 0 to whatever the y value of this point is. So we are at a general value x here, which lies between -1 and +1. The y value of this point is 0. Well, to get the y value of this point here, we need the equation of the unit circle. Now, a circle centered at the origin with a radius of 1 has the equation x squared plus y squared equals 1. That just comes from Pythagoras' theorem. We've radius of 1, point xy. This distance here is x, this distance is y. Square these and sum them will give us the squared hypotenuse. So that's straightforward enough for a circle centered at the origin. X squared plus y squared equals r squared, where r is 1 in this case. If we want the y value of this point, we just rearrange this to get y equals the square root of 1 minus x squared. Now we want y to be positive, so we are only considering the positive square roots here. Okay, we're only dealing with the part of the unit circle that's above the x-axis. So we consider a cross-section of the volume under the surface 5x squared y in this direction. So we know what to do. We just integrate from y equals 0 to y equals root 1 minus x squared, the function, okay, with respect to y, of course. So that'll give us the area of the cross-section. So we have to start by getting this integral in here. So we're integrating this with respect to y. We treat x as a constant, so 5x squared will appear in this. It's multiplied by y, integrate y with respect to y, we get half y squared, so we end up with a 5 halves x squared y squared, and we apply our limits. So we plug root 1 minus x squared in for y. If we square that, we get rid of the square root. And then we have a minus sign. Plug 0 in for y, that'll give us 0. So we just end up with 5 halves x squared times 1 minus x squared. So that's the area of a vertical cross section of the volume. Okay, for a general point x between -1 and +1. So we know what to do. We then consider slices of width dx, and we get the volume of each slice by multiplying the cross section by the width dx. Okay, so the cross sectional area is 5 halves x squared times 1 minus x squared. We multiply by dx and we just sum those from -1 to 1. So this is a straightforward integral. We don't need any substitution method here. We can just multiply this in and integrate term by term. And our limits run from -1 to +1. Now in part B, we are going to repeat this calculation, but this time for a different function. Now this is just a constant function, f of x comma y equals 1. So of course the z-axis is coming out of the screen. The positive z-axis is coming out of the screen. So basically for each point in this shaded region here, the z or f value is going to be a constant. It's going to be 1. So if I draw a rough sketch of the situation, we have half a cylinder with a height of 1. Okay, so this circle here is supposed to be this here. I'm trying to show it with some perspective. So this line here is the x-axis, and this line here is the y-axis, and the positive z-axis of course is in this direction. Okay, so we want the volume of this shape here. Well, since it's half a cylinder, we can do that without any integration. We just get the area of the semicircular base, which is a half pi r squared, half the area of a full circle, pi r squared, where r is 1 in this case, and we just multiply by the height, which is 1. So this is the area. So the volume is going to be, well, the area of the cross section, half pi times the height 1. So we should get a half pi, or pi over 2. So here's the calculation using double integrals. So instead of 5x squared y, we have 1. So we have to integrate 1 with respect to y. Well, that's just y. Okay, the integral of 1 with respect to y is y, and here are our limits. We plug root 1 minus x squared in for y, then minus sign, then 0, and we just get this here. So that's the area of a cross section. And we have to consider slices then of width dx, and to get the volume we just sum all those slices from -1 to 1. So we have to integrate root 1 minus x squared. So let's run through how to do that again. We use the substitution x equals sine of theta. Well, we could also use x equals cos theta, but I'll use x equals sine theta. If we differentiate x with respect to theta, we get cos of theta. So dx is cos of theta times d theta. Now 1 minus sine squared theta is cos squared theta, and the square root of cos squared theta is cos theta. So this quantity is cos theta, and we have cos theta times cos theta. That's cos squared theta. Okay, so you can look up that identity in tables. It comes from cos squared theta plus sine squared theta equals 1. Alright, let's get our limits. So when x is -1, what is theta? Well, in degrees, theta is 270 degrees, but we want everything in radians. So that's 3 pi over 2 radians. 3 times 90 degrees. 3 times pi over 2. Okay, we're in a quadrant where the sine function is negative. If x is 1, we see that theta is 90 degrees, or pi over 2 radians. Now we need to use an identity for cos squared theta. This is the one we use. Half into 1 plus cos 2 theta. Integral of 1 with respect to theta is theta. The integral of cos 2 theta is, well, the integral of the cos function is the sine function, and we divide by the coefficient of theta. If we plug all these limits in, we end up getting an answer of minus pi over 2. Well, we should really be getting a positive answer here, because you know, the function is positive. F of x comma y was equal to 1. Okay, f of x comma y was equal to plus 1, not minus 1. We will actually get a positive answer if, instead of using 3 pi over 2 for theta in our limits, we'll get a positive answer if we use minus pi over 2. The sign of minus pi over 2 is the same as minus sine pi over 2, or minus 1. Now if we redo the calculation, we plug minus pi over 2 in for theta, and we are subtracting, of course, so we get minus pi over 2, or plus pi over 2. Over here we'll have a half sine of minus pi. Well, the sine of pi is 0, so the sine of minus pi is 0. So we will end up getting an answer of plus pi over 2.